Calculus. This is section 5.3, number 10. And in your textbook here, I'll read it out. It says, a rotating light on top of a lighthouse sends out rays of light in opposite directions. As the beacon rotates, the ray at an angle theta, right here, angle theta, makes a spot of light that moves along the shore. So let's say that it's kind of moving in this direction along the shore as the angle moves in a positive direction, okay? The lighthouse is located 500 meters from the shore, so from this point to this point, from the shoreline, and it makes one complete rotation every 2 minutes. Okay, so first things first, we have a right triangle here, don't we? Here's the beacon, the lighthouse there, there's the shore. It's a 90-degree angle here, its closest distance from the shoreline, and then we have just a random point in time that would complete this triangle, and so this would be D. And so because it is moving, but you can envision the triangle at an instant in time so that we can kind of work with it. So we're going to deal with the time in a few minutes, but in a few seconds even. But anyway, so we have this triangle, so we have theta, we have an opposite side, and we have an adjacent side. So obviously we can look at doing something like this. We can go tan of theta equals the opposite side over the adjacent, or that translates into let's do it down here, D equals 500 times tan theta. Okay, so that's great, except A says determine the equation of D as a function of time. So this is the tricky part. This is the tricky part. This is theta, and we don't want theta, we want t, something t. Okay, so some information here. Okay, so think about this. The beacon has a light shining in both directions. So as this ray of light, this one right here, as it passes along the shore and leaves, the other one comes along and meets this point at half the time, half the total time. So think about that. So in 2 minutes, one beam of light would take the whole 2 minutes to come around to the first spot. So the period length would be 2 minutes. But because there's two beams of light going in either direction, right, one up and one down, that means that the light comes back to the same spot in only 1 minute. So think about that. So think about the period length for tangent, we know is pi over b. And we're going to want to put b in with our variable. What's the variable? Well, it's going to be time. So let's think about this PL. Okay, so period length is now 1 minute because of the nature of the double-sided ray. So I'm going to go, let's just do it over here. So 1 minute is pi over b. Okay, so that's 1 minute pi over b. So b is pi over 1, or just pi. So b is pi. Now b is pi, and of course our variable is t. And so, yeah, you think about this is pi units per minute, let's say, if you want to think about it like that. Pi per minute, pi degrees, or sorry, radians per minute. And so we want to find out, you know, what's happening every minute. So you would have to multiply that. So that's where we get pi t. So theta, actually in terms of t, is pi times t. So we get this for our equation for A. 510, and it's pi t. Okay, and you can put brackets there if you want. All right. So that's how we get from theta to pi t, and that's the trickiest part of this question. If you graph it, so what do you want to know when you graph it? You can throw it on your graphing calculator or Desmos or whatever you want, but remember the nature of tan. Right, there's no plus or minus anything here, so this point does pass through the origin, right? And remember that we have an asymptote at half of the period length on either side of the zero here. So what's the period length we said was pi, right? Period length is, the period length is 1. So that means that at 0.5 we have an asymptote here, and negative 0.5 we have an asymptote here. Okay, and that's where we see on this graph. And then the other part is this 500. So if you go from the 0, if you go halfway between the asymptote and the 0, that's sort of like a quarter or 3/4 of the way through the period, and then you go up exactly a unit. So that's why we have 500 here. And I mean, just a rough sketch, that's all you need to do. Just show sort of one period. You can start at 0 and go to the first asymptote. Now why would we do that? Because if you think about it, it takes 1 minute for a ray to come back around to the original spot. And if you think about this ray of light, okay, so it's here on the shore, then it's over here, then it's over here, then it's over there, and at pi over 2, when this is 90, it's not on the shore at all. So that's where your asymptote is at halfway through the period length. Okay, so that's period length is 1, and at halfway through you have this asymptote. So you'd really only need to draw, this much of it, I guess, really. Okay, and then I just explained C, I guess. The significance of the asymptote is that's when the ray of light, or the beam of light, is exactly parallel to the shore, and so therefore distance is infinite. I guess you could think of it as infinite, because here it's pretty close, there it's quite far away, here it's like extremely far away from this point, so D is really large, and then at this point D is infinity, really, because it's not shining on the shoreline. Okay, so that is question number 10, 5.3. Hope that helps.